My name is Noel and I'll be presenting a measurement technique for measurement of inductance and resistance using a sinusoidal excited direct digitizer circuit. So as you are all aware, inductance is a basic element or inductors are basic elements which are used for measurement of strain, pressure or displacement in heater coils in inductive circuits in cookwares and precision control applications. And two important parameters which are used to characterize an inductive element are its inductance as well as resistance. So you can see that as the frequency range increases, the impedance is basically it's a function of the resistance as well as the inductance. So at higher frequencies it's dominated by the inductive impedance, and the lower frequencies it is dominant because every coil has some material and it's got its own resistance, so it's dominated by its own resistance. So the objective of this paper is to find out a novel technique for measurement of both inductance as well as resistance of inductive elements. If you ask me, are there no other methods? Yes, there are a lot of methods already available and existing in this world. I'll just highlight on those methods and what are their disadvantages or what else is involved in those, and what am I trying to propose over here. So the traditional conversion techniques basically consists of bridge-based measurement techniques. As you can see over here, where you have certain inductive elements in a bridge-based combination, but these require additional digitization-based circuits, and they do not measure the resistance of the coil, and they require additional demodulator and ADC circuits for digitization. If you look at the certain other examples of the Maxwell-Wien bridge-based schemes, where the unknown inductance and resistance can be found out by a variation of capacitance and resistance, but still it's a bridge-based technique, and then further it's an analog-based measurement scheme, and you have to have certain other demodulators and ADC schemes for digitization. So there's a lot of other circuit components also involved in these things, and this is a modified Maxwell-Wien bridge scheme for obtaining the inductance as well as resistance and to take care of the stray capacitances. But it also requires manual tuning of this capacitances and resistances to obtain the bridge balance, and also requires additional demodulator circuits again. So if you look at various other techniques are the LC based tank oscillator circuits, the resonance circuits. When you get the peak resonance, you are able to find out at what point your circuit is operating in it, and you get to find out the unknown value of inductance. But here also you don't get a measure of the resistance of the coil, and it requires additional circuits for digitization. There are certain other techniques which are, and if you see the digitization schemes in most of these schemes for the LC oscillator based circuits also, there's a peak detector followed by a lot of digital buffering and low pass filtering, followed by multi-channel ADCs to process each of these elements which go to a processor. So you can see that other than the front end circuit, there's a lot of circuit required to make the final output into a digital state. And there are a lot of FFT based conversion techniques also, but most of these are only concerned with the frequency component, which is modulated by the inductive portion alone, and you're not able to measure resistance. It also requires additional circuits for digitization, and it's a process intensive because you have to have a lot of lookup tables or some kind of algorithm running inside a processor to find out the actual value of inductance later. There are dual slope and single slope based conversion techniques also, but which have been reported earlier in IEEE journals, but these also require a lot. Of course, this is a pure hardware based circuit, and it gives a digital output, but it does not have a capability to measure the resistance of the coil. So the objective over here is to measure both L and R using a hardware circuit alone. The final output. Okay. So the objective is to measure both L and R in a digital format without using any conventional ADCs. Okay, there's nothing wrong in using an ADC, but it's an additional element, a VLSI element sitting inside your circuit. So what if you could have all of it in the analog domain itself? You could have a faster measurement technique possible. So this is just a concept for measurement of both L and R using a sine wave. So there's no need to get frightened by the circuit. So it basically consists of voltage to current converter, which is formed using these op amps OP1 and OP2. That's the portion. Then you have an analog switch based phase sensitive rectifier, that is based on the phase of the sine wave. You decide how these switches are to be operated, whether it should be in the sine component or the cos component should be either taken into picture. So that is formed using this S1, S2 and this OP3 inverter. then you have a dual slope front end. Basically the technique used over here is the normal dual slope concept, where in the dual slope you have an integration cycle where the unknown voltage is first integrated for a particular period of time, and then you deintegrate using a constant reference voltage. But that technique is being modified over here using a sine wave itself, and without having any other constant sources, you should be able to obtain the unknown value of L and R itself directly. Then you have a sine cos based switch control circuit, which is also formed using this one circuit. It basically consists of a sine wave going to a integrator circuit which gives a cos wave output over here, and then you get a cos wave and a sine wave and its basic digitized square waves. I will come to the details. So it works on a modified dual slope conversion technique and requires two phases of conversion, the integration phase and the deintegration phase, and it provides a direct digital output. That is, once the conversion cycle is over, you don't have to do any further processing on it. The data in terms of the time interval or the counter frequency pulse counts is proportional to the unknown inductance and resistance. So if you look at the integration, which statement? The last one. So the moment the dual slope conversion is basically based on the time interval for the conversion. So once the integration cycle is over, then you start deintegrating using a constant voltage in the normal case of the dual slope. But here I'm using that philosophy itself, but in a different way, without having a constant reference voltage. I make use of all circuit parameters itself to eliminate most of the dependencies on the circuit parameters which have occurred during the integration cycle. And the digital output that you get is basically a digital count output. So my L is going to be proportional to a number of digital counts. So the processor, I can use that inside my processor in a different way. So basically getting a digital output for digital processing is getting a number of bits. So it's like a number of counts for me. So that's what I meant. So during the integration cycle, the switch is this SC3 is kept low, and you have it the switch selects the unknown element over here, and similarly you have this integrator is also set to this position. So what basically happens is you have the sine wave over here, the sine wave, and you have the output VOC1 is basically it's a comparator based circuit, zero crossover detector. So you have a square wave of that. Then you can see that this portion is an integrator. So when you integrate a sine, you get a cos wave, and you get a zero crossing over signal for that also. So this blue square wave and the red square wave are the outputs which I am going to use to control my particular switches. Now if you see, this is going to a current V to I converter, which will give me a current of which is proportional to this divided by this particular value of R0, which is any value that you can put based on the range of measurement that you are going to use. So now you are going to get, when that current goes on to is applied to the unknown element, I'll just come to the equation. This is how it looks. The voltage developed across the unknown element is going to be L into di by dt plus I0 into Rx. So you get a function of cos as well as a function of sine over here. The cos component contains the terminology of the unknown inductance. The sine component contains the term of the unknown resistance of the element. So going back, yeah. So this is how the waveform would look like, and it consists of two portions, which is proportional to the sine component and one proportional to the cos component. Then what I do is I will use my switching waveform, the SC1 as well as the SC2 outputs, in order to switch this voltage, and I'll get two rectified outputs. I'll get two rectified outputs. One which is going to be, this is just shown like this for easiness of representation, but this is not the way it's going to actually look, because once you rectify this with respect to this particular waveform, it's going to look slightly differently. Just for illustration, I have shown Vrx is going to be proportional to the sine portion, and Vlx is going to be proportional to the cos component. So you get a rectified output of this. Now usually what the dual slope works on is a constant voltage, but here I am not interested in any more constant voltage. I will work on this on this rectified waveform itself and integrate it using my second stages in order to get an integrated value which is going to be proportional to the unknown Lx, and an integrated value using the second stage which is going to be proportional to the unknown Rx. So basically the integrator output of OP4 is going to be proportional to the Lx term, this particular term, and this is, yeah. So then during the deintegration cycle, I choose a particular reference resistor. Instead of a reference voltage, in my case, I am choosing a reference resistor which is a fixed constant value, and I repeat the process again, but at this time the deintegration voltage which goes to both these integrator circuits are the same. So what happens is you have the voltage developed across this is going to be I0 into RF, which is this particular voltage which is proportional to sin omega t, and then I'll use the same switching sequence again to control my switches such that without any other switch control I can get a deintegration waveform. So you integrate in one direction and you deintegrate, and this time is now going to be proportional, as on final computation you can get that it's going to be proportional to the value of the unknown inductance, and the second time that you obtain from this output of this comparator is going to be proportional to the unknown Rx. So the only other terms, as you can see over here, on which this output depends is the value of the reference resistor, the frequency of the sign excitation, and the integration time interval. So all these can be manually fixed. So if you look at the output, what are the factors on which the output depends upon? It is almost, as you can see from these equations, it is independent of the excitation or the voltage fluctuations. So if there is the sine wave over a particular cycle, if it varies also, there is no concern. Or a conversion cycle, if it as long as it remains constant within a particular conversion, even if the next amplitude goes down, there is no much concern because the final output is going to be independent of that. You only need to have a precise value for this R reference value, and you need a sine wave which has got a constant frequency. Even if there is a drift in that frequency, there is no concern because finally the integrator stage is going to average it out. So in that way, as long as you have f plus average and f minus average within a cycle, there is no concern. So we are able to get a direct digital output for the inductance as well as resistance. This work has been, we have also carried out the theoretical simulation as well as hardware implementation for this, and yeah, it's found to be linear, sir. So we have been able to demonstrate a method for a different technique for measurement of inductance as well as resistance.